curiosity often ignites the flame of discovery. Our story begins with three such sparks: Susumu Kitagawa, Richard Robson, and Omar M. Yagi. Each of them distinct in their origins and journeys, but united by an insatiable curiosity for the world of chemistry. Growing up in Japan, Susumu Kitagawa found himself captivated by the invisible forces that shape our world, drawn early on to the magic of molecular structures. This fascination led him to a career in chemistry, where he delved deep into the mysteries of the atomic world. In another part of the world, Australia, Richard Robson was weaving his own narrative. An innate problem solver, Robson found in chemistry a playground of puzzles waiting to be solved. His interest was piqued by the potential of creating structures at a molecular level with potential applications that could change the world. Meanwhile, over in the United States, Omar M. Yagi was embarking on his own scientific journey. Born to a humble family, Yagi's passion for chemistry was ignited by a high school teacher who saw in him a spark of potential. He went on to explore the realm of chemical structures with a fervor that would later lead him to groundbreaking discoveries. These three curious minds began experimenting, each in their own labs, their own countries, driven by the same relentless pursuit of understanding. They were drawn to the potential of molecular structures, the building blocks of our world, and the fascinating possibilities they held. Their early experiments laid the groundwork, sparking a fascination with porous crystalline structures known as metal organic frameworks, or MOFs. The potential of these MOFs, with their ability to trap gases and harvest water from desert air, was just on the horizon. Their curiosity was just the beginning of a journey that would change the world. Little did they know their individual sparks of curiosity were about to ignite a flame of discovery that would illuminate the world of chemistry and beyond. For science is a collaborative effort, with each discovery building on the last. Imagine for a moment a world of molecules where tiny building blocks come together to form intricate designs. This is the world that Richard Robson began to explore, laying the foundation for a revolution in chemistry. Robson, a visionary in his own right, was fascinated by the concept of metal organic frameworks, or MOFs as they're commonly known. Now let's break it down. MOFs are like molecular sponges. They are porous, crystalline structures composed of metal ions or clusters which are connected by organic molecules. Picture a honeycomb. Each cell a room of its own, interconnected yet distinct. This is similar to how MOFs are structured, and the metal ions or clusters form the corners of each room, while the organic molecules act as the walls. But what made Robson's work truly groundbreaking was the nature of these rooms. They were not just empty spaces. They were porous. Imagine a sponge full of tiny holes that can absorb and hold water. The porous nature of MOFs allows them to trap gases, harvest water from desert air, or even capture carbon dioxide. Robson's pioneering work illuminated the path towards creating functional materials with huge internal surface areas. It was like he had discovered a new way to play with Lego blocks, a way that could change the world. His research offered a blueprint, a foundation on which future scientists could build. It was a testament to the power of curiosity and the pursuit of knowledge. It was a stepping stone towards a future where molecular architecture could be used to tackle some of the world's most pressing issues. Yet, like any foundation, it was not an end in itself. It was a platform, a launching pad for further exploration and discovery. Robson had laid the foundation, but there was still much to be built. With a strong foundation, Kitagawa and Yagi were ready to build. Like architects of the microscopic, they took the baton from Robson and ran with it, pushing the boundaries of what was possible with metal organic frameworks, or MOFs. Susumu Kitagawa, hailing from Japan, came up with new ways to control the size and shape of the pores in MOFs. This allowed him to create structures with massive internal surface areas, akin to fitting a football field inside a sugar cube. This was a game changer. Suddenly, MOFs weren't just interesting molecular structures, they became functional materials with incredible potential. Meanwhile, Omar M. Yaghi, from Jordan, took a different tack. He pushed the envelope on what materials could be used in the construction of MOFs. With his team, he developed a wide array of MOFs using different metals and organic molecules, each with unique properties and potential applications. His work was like unlocking a molecular toy box, full of new and exciting building blocks. But Kitagawa and Yagi didn't stop at creating these impressive structures. They sought practical applications for their work, and they found them. MOFs, it turns out, are excellent at trapping gases. They can be used to harvest water from desert air, providing a potential solution for water scarcity in arid regions. They can capture carbon dioxide, a greenhouse gas that contributes to climate change. Their work had profound implications for a range of industries. For instance, MOFs could be used in gas storage and separation, which could revolutionize the energy sector. They could also be used in drug delivery, opening up new possibilities in the field of medicine. Kitagawa and Yagi's work was groundbreaking. They expanded on Robson's foundation and took MOFs to new heights, transforming them from a scientific curiosity into a practical tool. Their innovative work was transforming MOFs from a scientific curiosity into a tool for tackling global challenges. They had built on the foundation, and the building was only just beginning. From the laboratory to the real world, the impact of these molecular sponges is profound. Imagine microscopic rooms, porous and crystalline, with a capacity to trap gases, harvest water from desert air, or capture carbon dioxide. These are not just theoretical constructs, but tangible, functional materials developed by Susumu Kitagawa, Richard Robson, and Omar M. Yagi. Let's delve into some of their real-world applications. Picture arid regions where water is a scarce commodity. These molecular sponges can literally pull water from thin air, providing a lifeline to communities living in these water-starved areas. It's a game changer, using the power of science to solve one of humanity's most pressing challenges: water scarcity. But the benefits of these molecular sponges don't stop at water. They're also stepping up to the plate in the battle against climate change. These materials have the ability to capture and store carbon dioxide, a key contributor to global warming. By trapping this greenhouse gas, we're not just reducing its presence in our atmosphere, but also exploring its potential reuse, turning a harmful waste product into a valuable resource. And let's not forget the clean energy sector. The energy storage capabilities of these molecular architectures are opening new horizons for renewable energy sources. They're helping us store energy more efficiently, making wind and solar power more reliable and accessible, even when the sun doesn't shine or the wind doesn't blow. From providing water in the desert to tackling climate change and advancing clean energy, the applications of these molecular sponges are as diverse as they are transformative. They're not just about advancing our scientific understanding. They're about using that knowledge to improve lives, communities, and our planet. The story of Kitagawa, Robson, and Yagi is a testament to the power of scientific collaboration and ingenuity. Their work was not just about science, but about using science to make a difference. The story of MOFs is far from over. As we cast our gaze into the future, it is clear that the potential of metal organic frameworks, or MOFs, is vast and largely unexplored. The porous, crystalline structures of these molecular marvels are primed for a multitude of opacnons, and the world of science is only just beginning to scratch the surface. Consider the realm of energy storage. With the ever-increasing demand for cleaner, more efficient energy sources, MOFs could play a pivotal role. These molecular sponges, with their massive internal surface areas, could potentially store hydrogen or methane for fuel cells, making clean energy more accessible and practical than ever before. Or take the field of medicine. Imagine a world where targeted drug delivery is the norm, not the exception. MOFs could be engineered to carry and release drugs within the body with pinpoint accuracy, revolutionizing treatments and improving patient outcomes. And let's not forget about environmental applications. We've already seen how MOFs can harvest water from desert air and capture carbon dioxide. But what if we could push these capabilities even further? What if we could use MOFs to clean up oil spills, or even to filter microplastics out of our oceans? The possibilities are as vast as the structures of the MOFs themselves. As we speak, scientists across the globe are working tirelessly, building upon the foundations laid by Susumu Kitagawa, Richard Robson and Omar Yagi. They are exploring new ways to synthesize MOFs, to manipulate their structures, to enhance their properties. They are pushing the boundaries of what we thought was possible, and in doing so they are reshaping our world. The work of Kitagawa, Robson and Yagi has opened a door to a future full of potential, a future where science is not just about understanding the world, but also about improving it